Hi class. So we've been learning about 3D and perspective and how, the idea that things as they get further away get smaller and they go towards the vanishing point. So let's start shifting now from this idea toward how do we actually make it work? So how do we actually calculate our perspective? So the first thing I'll do is I'll draw out this scene that we've been working on. Kind of like that. And I have my near plane and I have my far plane. Now I'm going to do a few things. First, I'm going to draw 2 points in the scene, one closer and one further, but at the same x and y coordinate, just different z's. And I'm going to note, the first thing you'll notice, if I draw my line to them, the one that's closer is higher up on the raster. The one that's further away is lower down. In fact, if I draw a third line here, like the center line, the further it gets, it actually approaches that center line, just like we learned about with our vanishing points, okay? So as the z increases, then x, y, they tend toward 0, 0, which is our vanishing point. Okay, so if we have a bigger z, basically closer to 0, just like that. So as z gets bigger, it gets towards 0. Can you think of a way to make a number that as z gets bigger, the number gets smaller? All that we do is we divide. We divide x and y by our z. And this simulates this perspective. So now, I guess what I didn't say earlier is these points, they project, let's not do that, on my image plane here at different spots. And I'll just highlight that now. This is my image plane. Okay, and for any point on there, then my x in my view, my x on the image plane, x on the screen, is just going to be my x in the world. So if this point here is a x world, y world, z world, then it's going to be my x world divided by my z world. So this is my screen coordinates. This is my world coordinates. So I just take my world coordinate, I divide it by the z, and you get that effect. As z gets bigger, my number gets smaller. It goes towards 0. It'll go towards that vanishing point. And of course, y works the same way. So that's pretty cool. So all I got to do, and if you go back and look at some of the early examples that I would have posted or to do some early projection, you would have seen that there's definitely a divide by z in there. Now, of course, the first question that should cross your mind is, that's pretty cool, but how do I do a division with matrices? So it actually is non-trivial at first. So how to do this with matrices, right? And I don't want to just do a division because I can multiply by -1, or divide is not hard. I want to divide by part of my coordinate. So let's just spell this out here. I have my coordinate x in the world, y in the world, z in the world, and 1. And I want to do something such that my x gets divided by that. And it turns out that you can't really do it directly with a matrix. I can't have something in the point impact something else in the point in that kind of way with a division. Only with addition and subtraction. But luckily, because we're doing homogeneous coordinates, there's a way to do it. 1, 0, 0, 0, 0, 1, 0, 0. So far, our x, and this is going to be my screen coordinates, okay? So far, we have x, w, and then y, w. So far, nothing has changed, right? And then 0, 0, 1, 0, right? Nothing has changed. But this is where things get interesting. 0, 0, 1, 0 there. We don't put things down there, do we? That's kind of weird. But I just did. What happens is, this is the y coordinate. So instead of just keeping y at 1, here what happens is, w coordinate, I said y. W coordinate. Here, 0 times xy, okay. 0 times y, w, 0 times xw, 0 times yw, but I put my zw in here. Okay, that's weird. So we don't like working in homogeneous coordinates if the w is not 1. So of course, the first thing we do is we divide by w. So this becomes xw over zw, yw over zw, zw over zw, and then zw. Now, how cool is that? So as soon as I normalize from a homogeneous coordinate into my regular plane, regular coordinate system by dividing by w, making it 1, I get that free, well, not free, I have to do it, but we get that division by z that we expect, that we were looking for. So this is my coordinate here to make it divide by, my matrix rather, to make it divide by z. There's a couple of problems here you might not be noticing, but the first problem is kind of tricky. And that problem is that in a right-handed system, okay, z goes to me. If I'm going to the scene, the z is negative. Uh-oh. So z is negative into the scene. Right? And this will make x and y negative. Am I zoomed out? No, I'm good. This makes my x and the y negative, right? So instead of just shrinking it in, I shrink it and they get flipped. X goes the other side. That's not what we want, right? It's like a mirror image. So you could do absolute value, but this gets all messy. It turns out that since we're in a right-handed system, we assume we're always looking down the negative z-axis. We just fix it. Just use negative z. So I'm going to change this 1 here. I'm going to write it in red so you can see it easily. Negative 1. If I do that, then all of these things, this becomes a negative down there. I divide by negative, I divide by negative. Okay. And now this equals xw over minus zw, so it'll be a positive number. Yw over minus zw. Cool. This becomes minus 1, and it becomes 1. But you know what I'm going to say? I'm going to say let's forget about z for now. Okay, let's forget about it for now, and we'll come back to that in a later lecture. Basically, because I'm putting onto a screen anyway, at this point I just want x and y, so let's figure out fixing z at a different time. Negative 1, that's kind of weird. Okay. Maybe you could think it that I'm at the image plane is 1 unit in front of me. Okay. And then negative 1 on there. Okay, we could think of it that way, I guess, but basically don't worry about it. There's another problem. And this is that the x and the y, they actually go to 0 very quickly. As z gets bigger, they shrink very quickly. Just think about it. If z is 1, there's no change in x or y. Okay. If z is 2, just 1 unit further away, bam, gets double, half the size. Okay. Z is 3, becomes a third. So if I'm in a 100 by 100 by 100 space, very quickly the front is useful, and then bam, as I move 1 pixel in, I lose half the screen real estate. Okay. So one way you can fix that, I'm gonna repeat what I just said in case it wasn't clear. If I have like a 100 by 100 screen with 100 z depth, as I move 1 out of those 100 pixels into the screen, I'm already x and y are half in. I've lost that outside half of my screen. As I move to 100, it all crowds in the middle. And this is because of basically a field of view. But first, I'm getting ahead of my notes here. One thing we can do is we can move into scene move the object into the scene to get better control. But then you start fiddling and twiddling with numbers. And the real solution is to think of this as a field of view problem. Okay? And a field of view is the degrees that you can see here. So if I draw out my field, if I draw out my scene again, here's my eye over here. I'm going to draw two lines. Here's a green line. You know, I'm going to draw this differently. I'm going to do this differently. Yeah, okay. This is what I get for thinking on my feet. Okay, imagine now I have, yeah, third try is the charm. And imagine I have an image plane this big, okay? And imagine this is my model. Now you can see it's a very narrow field of view. This angle here is narrow. It's a narrow field of view. Now, at the same distance from me, if I have a bigger image plane, look at that, I can see more things in my scene. If I have a sphere here and a sphere here, you can see the green field of view sees them completely, but in the black field of view, they're very narrow. So properties of the image plane, so how far away it is, how big it is, those kinds of properties, this impact how much we see. This impacts, and the impact that Z will have. So we can fix this problem and have control over this problem if we rethink of things in terms of our field of view. So what we want to do is we want to start learning how to model the field of view mathematically. And that's basically what we're going to do. So I'm going to stop here, but we're going to now work through the math of how to solve this perspective, and through it you'll see how we don't have to worry about this problem. We can get control over it by using math to solve for our field of view. All right, so we'll take a pause there.